Alright, we're going to continue with section 15.8 in this video, and we are going to do number 15 on page 1061. Oh, and before I forget, on the last problem that I did, which was number 11 on page 1060, although we didn't need these bounds, when I started writing up bounds, I wrote the intersection of three things. I should have just written the three things, so it should have been a cylinder, the plane x equals 0 and the y equals 0, not the intersection of the three. We do intersections sometime, but on that particular problem, I should not have written intersection. It should have just been the cylinder and the two planes making up our sides. So for this problem, our directions are saying exercises 9 through 23, use the divergence theorem to compute the surface integral over sigma of f dot n ds, where n is the normal to sigma that is directed outward. All right, so and they give us our vector field here, f of x, y, z equals x squared, comma y squared, comma z squared, x squared, comma y squared, comma z squared. Sigma is the boundary of the solid region inside the cylinder. X squared plus y squared equals 4, and between the planes, z equals 0 and z equals 2. All right, so we have just a portion of a cylinder, and that cylinder has radius 2 and centered at the origin. All right, so first, now I sketched the solid in our previous problem, but when we evaluate triple integrals, we don't tend to sketch the solid over which we're integrating. We just project it down into the xy plane and sketch that. So from here on out, that's what our sketches will be, the region in the if we were to take our solid and project it down into the xy plane, or another plane for that matter, if you want to. If you could project it into the yz plane or the xz plane, any one is fine. We just tend to project into the xy plane. So first, let's find the divergence of f. So remember, oops, it's not a vector first off. The divergence, we take the partial of m with respect to x, we get 2x, plus the partial of n with respect to y, so plus 2y, plus the partial of p with respect to z, so plus 2z, and that's going to be our integrand. And then we need to look at our region D over which we're integrating. So we're integrating over that portion of the cylinder. So we take that cylinder and project it down into the xy plane. We would have this region in the xy plane where our radius was 2. Yes, our radius was 2. So now if we set up our region D, we can do it in rectangular coordinates, or we can do it in cylindrical coordinates. Cylindrical coordinates will be the easier of the two. So since we're going to do that in cylindrical coordinates, we'll skip doing the top, bottom, and the sides, because we did that mostly when we were working with rectangular coordinates. So here, if we look at this region right here, this region says that our r is going to vary from 0 to 2. Our theta is going to go from 0 to 2 pi. And then z, which is going to vary between 0 and 2. So actually, I will write it out that way. So d equals a set of points r, theta, z, such that r goes between 0 and 2. Theta goes between 0 and 2 pi. And z goes between, I keep forgetting, I think it was 0 and 2. Yeah, 0 and 2. So that's our region D. So those are going to be the bounds for our triple integral. So now the divergence theorem tells us that the surface integral over, textbook calls it S, sigma, I'm going to call it S, of f dot n ds equals the triple integral over D of the divergence of F dV, which for us equals, so we have theta is going from 0 to 2 pi, r is going from 0 to 2, z is going from 0 to 2, and our integrand is 2x plus 2y plus 2z. So, but remember, we're switching to cylindrical coordinates, so our x is equal to r cosine theta. So we have 2r cosine theta. Our y is equal to r sine theta, so plus 2r sine theta, and then plus 2z plus 2z. And when we do cylindrical, we need our Jacobian r, and then these are z's, so dz, and these are r's, dr, and d theta. So dz, dr, d theta, sorry. You can see that there. And then we go through and distribute that r and evaluate that integral as usual. All right, so let's look at another example. We will do number 23. So just to, again, let me just explain how this would go if we weren't using the divergence theorem. You would end up having to parametrize the top of the cylinder, which is just a plane, which is easy, the bottom of the cylinder, which is a plane, which is easy, and the sides of the cylinder, which is also fairly easy to parametrize. You would then have to evaluate those three surface integrals though over those three surfaces and then add them together. The divergence theorem makes that much faster. You don't have to parametrize any surfaces at all when you're using the divergence theorem. All right, so next, number 23. So number 23, same directions as number 15, and our vector field that they give us is f of x, y, z equals x times the quantity x squared plus y squared plus z squared. So x times the quantity x squared plus y squared plus z squared, and then y times that same quantity x squared plus y squared plus z squared, and then 0. So that's our vector field. And they tell us sigma is the sphere x squared plus y squared plus z squared equals 9. All right, so first let's find the divergence of f. X, I shouldn't distribute that x, but and that y. So the divergence of f is the partial of this thing with respect to x. So here we have x cubed, so that's just going to be 3x squared. And then x times y squared, that's just going to give us y squared. And then x times z squared, that's going to give us z squared. So that's just the partial of this first one with respect to x. Then plus the partial of this with respect to y. So plus here, y times x squared is just going to give us x squared. And then y cubed, that's going to give us 3y squared. And then y times z squared is just going to give us z squared. And then plus the partial of this with respect to z, which is 0. All right, so there's our divergence. And should we simplify? Yes, let's simplify this. So we end up with 4x squared plus 4y squared plus 2z squared. So that's going to be our integrand when we set up the triple integral. And then the region over which we're integrating is a sphere. All right, so the natural thing here would be to set this up using spherical coordinates. So the region D, our sphere was x squared plus y squared plus z squared equals 9. So here we do rho phi theta, where because our radius is 3, rho is going to vary between 0 and 3. And then because we have the full sphere, we're going to go from phi equals 0, the z-axis, all the way down to phi equals pi. The positive z-axis, all the way down to phi equals pi, the negative z-axis. And then theta is going to go all the way around 0 to 2 pi. So that's the region D over which we are integrating this. So now we set up our triple integral. And rho. So theta goes from 0 to 2 pi. Phi goes from 0 to pi. And rho goes from 0 to 3. And then we have 4x squared plus 4y squared plus 2z squared. And x is, we're going to put in our x, y, and z. But to save us some trouble, instead of writing in rho sine phi times cosine theta, and then for x, and rho sine phi times sine theta for y, and rho cosine phi for z, we can rewrite this as, so actually let's kind of unsimplify that a little bit. Let's take 2x squared plus 2y squared and write that. So we have 2x squared plus 2y squared plus 2x squared plus 2y squared plus 2z squared. 2x squared plus 2y squared plus 2z squared. This is just going to save us some simplification in our integrand, because this part right here, that part right there is just 2 times rho squared. Because remember, x squared plus y squared plus z squared in spherical coordinates is rho squared. So that saves us from having to plug in and try to do a bunch of simplification in the integrand. We can just do it a lot faster now with this. So then now you have to also keep in mind that x squared plus y squared in spherical coordinates is rho squared sine squared phi. So we're going to end up with 2 times, actually let's just take the 2 out here. So then we're going to end up with rho squared sine squared phi for this, with the 2 pulled out, and then plus, I've already pulled the 2 out of here as well. That's just rho squared. And then we need our Jacobian, which is rho squared sine phi. And these were rhos, so that's d rho. Those were phis, d phi, and those were thetas, d theta. And then we would just distribute, the rho squared sine phi and integrate that as usual. All right, so that concludes section 15.8. And what I will do in the remaining time is we'll review some problems from some past final exams.